Hello, and in this video I'm going to run through a quick example of the use of this concept of complex power. This is the circuit we'll be looking at. We have a voltage source here, whose voltage is represented by the voltage phasor VPH, and that is driving a load which consists of a resistor in series with an inductor. That gives us a complex impedance of R plus j omega L. I can work out the current flowing through this network just by dividing the voltage phasor by the complex impedance Z. That gives me the phasor representation of the current. In this case, that gives me this expression here, and I can just substitute these in to the formula that we derived last time for the complex power. That is the voltage phasor times the complex conjugate of the current phasor divided by 2. Well, the phasor representation of the current we've seen before. That's just equal to the phasor representation of the voltage divided by the complex impedance, which is here R plus j omega L. If I want the complex conjugate of the current phasor, that would then be equal to the complex conjugate of the voltage phasor divided by the complex conjugate of the complex impedance. But the complex conjugate of R plus j omega L is just R minus j omega L. If I substitute that back into here, I end up with a complex power, which is the voltage phasor multiplied by the complex conjugate of the voltage phasor divided by 2 times the complex conjugate of the complex impedance, which is R minus j omega L. Now, if you take any quantity and multiply it by its complex conjugate, you end up with the square of the magnitude of the quantity. It's most easily proved if you think in terms of the polar representation of a complex number, a e to the j theta, multiplied by its complex conjugate, a e to the minus j theta. These two terms cancel out. We're just left with a squared, which is the square of the modulus of the complex number. So I could write this as the modulus of the voltage phasor squared divided by 2 times R minus j omega L. And I can take that expression and work out its real and imaginary components, and that would give me the expressions that I've got here. This is the real component of the complex power. So that's the average amount of power that is being dissipated by this circuit. In this case, all of that power would be lost in heat in this resistor. This is the imaginary component of the complex power. So that's the maximum rate at which energy is being stored in the magnetic field in the inductor. Also equal to the maximum rate at which energy is being released from that magnetic field and going back into the circuit. I could equally well do the calculation not using a real and imaginary form for the complex impedance, but expressing it in polar form. And that would give me this type of result. It's exactly the same calculation. I've just produced an answer here in polar notation, showing the magnitude of the complex power and the phase of the complex power. You may note that the phase of the complex power is the same as the phase of the complex impedance. And that is always true, because you get the complex power by taking the complex impedance and multiplying it by a completely real quantity, the square of the magnitude of the current phasor divided by 2. We can see what this means and what this implies by looking at powers in the simulator. Here we have a simulation where the load is a series combination of an inductor and a resistor as before. And I'm plotting the voltage across the inductor and the resistor, as well as the voltage from the alternating voltage source and the current that's flowing through the network. Let's run it. Okay, we can see that the currents and the voltages are not exactly in phase for these components. and I can dial up the powers associated with the voltage source and the resistor and the energy that is currently being stored in the inductor. Right, let's go back to, let's say, this point here, where we've got a maximum value of our 7.5 volt voltage source. And with a maximum value of voltage there, the voltage across the inductor is, we can see, 1.565 volts, and the voltage across the resistor there is 5.93 volts. Not actually at its maximum. The maximum voltage across the resistor occurs a little bit later at this time here, and that's the time at which the maximum instantaneous power is leaving the network. The voltage across the inductor is related to the rate of change of current flowing through the inductor. So when the current is reaching its maximum value around about there, or the minimum value around about there, that's when the voltage across the inductor goes to its minimum value. It should, in theory, go to 0. You can see it's oscillating around 0 because I can't quite put the cursor in exactly the right place, but somewhere between there and there, the voltage across the inductor goes to 0 at the very bottom of the current curve there. The energy stored in the inductor is proportional to the current flowing through the inductor. So at maximum amplitudes of the current, like this one, or up here, we have the maximum energy being stored in the inductor. It's when the current goes through 0 that the energy stored in the inductor goes down through 0 as well. Now, there are occasional moments where you'll see that the current is going in there, around about there. The current is going in, if you like, the opposite direction from the 7.5 voltage source. The current is currently flowing left to right, this direction, but the voltage source here is at minus 1.739 volts. So this point here is actually below ground. And yet current is flowing out into the network in this direction, despite the fact that the voltage here is below ground. And that's happening because the voltage across the inductor is so large that it's adding to this minus 1.739 volts here and causing the voltage across the resistor to actually be positive. Still 1.64 volts positive, despite the fact that the output of the voltage source here is negative. And if the voltage across the resistor is positive, then the current flowing through the resistor must be going top to bottom, which means the current is flowing around this circuit clockwise. That means that at these particular intervals of time, the voltage source is actually absorbing energy. For most of the operation of this circuit, the voltage source is pushing energy into the circuit, and certainly on average, the voltage source is pushing energy into the circuit, but at these particular moments in time, the voltage source is absorbing energy. This can be a bit of a problem. For certain types of alternating voltage source, they're fine at giving out energy. They're not particularly good at taking energy back in and storing it at certain types of the cycle. It can cause problems in power networks. What we do about those problems, we'll be talking about in the next of these little lectures. It's something called power factor compensation.